percent composition, you have and you're told it's made up of this. Hydrogen 2.85 gram nitrogen. So what is the percent composition of each one? It's actually pretty simple. If the total weighs 12.04 and 7.34 grams of it is carbon, let's say sample, and you divide that out. If I said the fraction of this that is carbon is, if I divide this out, 7.34 minus 12.04. Three significant figures, 4, so I'm going to go 88.3736. Keeping those three, the 7 rounds the 3 to a 4. Divided by 12.04. Did you get it wrong? That's what you get. The grams cancel here, and this is fraction of sample to carbon. I guess if you wanted to put units on it, but usually we don't put units here. So the fraction of this sample that is carbon is 0.6096345. The fraction. You follow that? Maybe it helps if I said that would be three significant figures is that. Round this 09 to a 10. So 60.61.0% carbon. This sample is 61.0% carbon. Let me do it for hydrogen. 1.85 over the total. This is the total of the sample. These are the things that make it up. If you add these up, they add up to 12.04. For hydrogen, divided by 12.04 times 100 times 100. Rounding correctly, I get that. Percent hydrogen. And then for the nitrogen, 2.85 over 12.04 times 100. 2.85 divided by 2.85 divided by 12.04. So this is what it was for carbon. This is what it is for hydrogen, and this is nitrogen. You follow that? This is how much the sample weighs totally. And it's made up of this many grams of carbon, this many grams of hydrogen, and this many grams of nitrogen. If you want the percent, numerator, denominator tells you the percent carbon. Numerator, denominator tells you the percent hydrogen. Numerator, denominator tells you the percent nitrogen. Times 100. If you don't multiply by 100, then it's a fraction of the sample. You follow that?
Yes.
Okay. Percent composition another one. You just have a sample that's a total of that sample is made up of 3.01 grams of carbon, 4.00 grams of oxygen, 17.81 grams of chlorine. So what's the percent composition of each? For carbon, 3.01 over 24.81 times 100%. For oxygen, it's 4.00 over 24.81. And for chlorine, it's 17.81. Those both 81. So 3 over 24, 4 over 24.81, 17.81 over 24.81 times 100. It is that simple. I haven't lost you, right? You're just tired of class, right? It's hard to tell. 3.01 divided by 24.81. Correct significant figures are times 100. 12.1% carbon. 4.00 divided by 24.81 times 100. Oxygen. 17.81 divided by 24.81 times 100. These should add up to 100%. 690. Or close. Yeah, adds up to 100%. You follow that? So I have a sample, I'll just say it like this. I have a sample that's C something, O something, Cl something. And it weighs 24.81 grams. If you could isolate the carbon, the oxygen, and the chlorine into separate groups and weigh them individually, that's what we're doing. If I could split off all the carbon, however much it is, and weigh it on the scale, it weighs 3.01. If I could split out all the oxygen and weigh it, it weighs that. If I could split out all the chlorine and weigh it by itself, it would weigh 17.81 grams. And this weighed 24.81 grams. That's conceptually what's going on. You with me? Twist on this, what if I gave you this formula? Okay, now what's the percent composition? You can still do it by doing it in grams per mole. Carbon, there's 9 of them. Hydrogen, there's 8 of them. Oxygen, there's 4 of them. Carbon is 12.01. This is 1.01. This is 16.00. 8.08. This is 65. 64. That totally doing calculator. 9 times 12.01. 108.9. Really, that should be 12.01 times 9. So my calculator was, but I'm keeping 4 significant figures. So the 9 rounds to 0, so I did that one. Add them up, 8, 9, no. God. 108.1 plus 8.08 plus 64. I'm going to leave the grams per mole like that and say, here's the overall weight of this. We're just going to pretend we have 1 mole of it. It's if I'm going to be proper, 2 significant figures, 2 and 1. So 1 after the decimal, so that rounds up to the 2. So really I need to be using 2. So we're going to call that the total weight. We're just going to assume we have 1 mole, and then that works out. That means we have 180.2 grams. But I'm going to leave it as grams per mole because this works out just fine. All right. If I have this much carbon, this is grams per mole of carbon. That means I have grams per mole, 180.2 grams per mole. The grams per mole units cancel out, but that's what you expect when you're doing fractions or percents. So a different way of doing percent composition. One divided by 180.2 times 100. I gotta fix that for significant figures. 4 here, 4 here. I'm keeping those. That's the percent carbon that this molecule is. So the rest of this just looks the same as the previous problem. 8.08 grams per mole for hydrogen. Total weight is 180.2 grams per mole times 100%. 8.08 divided by 180.2 times 100. That was 3 significant figures, so I'm going to stop there. So I've got that for hydrogen. Got this for carbon. .00 grams per mole for oxygen, 180.2 grams per mole total. 64.00 divided by 180.2 times 100. Rounding properly, I get that. That was oxygen. And those should have 800. I got 99.98, but that's how the rounding works. Maybe I rounded it wrong, but you follow that? Different way to do percent composition. You're just given this, and that's all you're given. And you're asked the percent composition of this, this, and this. You do that whole thing with the periodic table. You with me? Do you remember this phrase? Remember that from the previous chemistry class? Let me show you conceptually what empirical formula is. I don't think I've explained the double bonds yet. Two variations that I want. Let's try. That's one. How's the scale coming up? 1, 2, 3. I don't think your book does this. Those are ugly hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15, 16, 17, 18, 19, 20. 5, 6, 7, 8, 9, 10. as a guide. It's 4 and 6, 7, 8, 9, 10, 12. That's 12. Good. I'm struggling with that. So it's just a string of carbons with hydrogens on it. So these on the outside are hydrogens, these are hydrogens, just in case it's not obvious. How many hydrogens are here? 1, 2, 3, 4, 5, 6. And there's 2 carbons. How many hydrogens are here? Is that 10? 3, 4. All right, 10. So I'm going to work that. How many hydrogens are here? 5, 10. That one's 12. 4, 5. I'll come back to that. I just won't go any further, but let me put it like this. What's the ratio of carbon to hydrogen? It's 2 to 6, which you can reduce down to 1 to 3. How about this one? It's 4 carbons to 12, which reduces down to 1 to 3, right? You divide 4 by 4, you get a 1. You divide 12 by 4, you get a 3. And then this one, I'm just not coming up with these structures quickly, but this one's 6, 18. You divide that by 6. Divide that by 6, you get 1. You divide 18 by 6, you get 3. So if you have a carbon, if you have this molecule, C6H18, the empirical formula of this is this, and the empirical formula of this is this. Meaning, this is a ratio of 1 to 3, and the smallest molecule you can make that has a ratio of 1 to 3 is this. So this is sort of like at the head of a family of lots of larger and larger carbon atoms. I can't use actually 4, 6. Can I do 8? Divide that by 8. This would have to be 24. I'm making up fictional things now, so I should probably quit. But if I had this molecule, this molecule, this molecule, let's say I did an analysis of this. I split the carbons out and weighed them. I split the hydrogens out and weighed them. And I found a percent by weight of this. You would have the same percent by weight carbon for here, here, and here. You follow that? Let me say it again. If I had this sample, which is fictional, I can't come up with the right formulas here. You can't make a molecule like this. But if I took this and I put it through analysis and I could separate all the carbon and separate all the hydrogen and weigh the carbon separately from the hydrogen, and I have my original weight for my original sample, this is just like the very first one of those compositions I did. You would find out whatever the percent carbon is and whatever the percent hydrogen is. If you did the same thing here, you find exactly the same percent carbon, exactly the same percent hydrogen. You did it here, it happened again. You get exactly the same percent carbon and the same percent hydrogen for all of these. And this one the same way. You get the same percent carbon and same percent hydrogen. This is the smallest possible formula you can make out of these, so that turns out to be the empirical formula. This is really kind of an antiquated thing, but back in the day when scientists would have a sample that they knew was just hydrocarbon like this, you can take it through an analysis called combustion analysis and find out how much carbon and how much hydrogen, and then figure all this out. But what you didn't know was whether you started with this, 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 or this. So all you could say it was in this family of empirical formulas. It was either this or this or this or this, but you couldn't tell which. These days we have much better analysis techniques to help us get past that. So it is kind of antiquated, but it's an exercise 12, 11 classes love. But I will come up with better examples for that, so it's a little more obvious. Apparently I'm just going to fade right out. Let's finish the empirical